The next property that we are going to see about systems is the time invariance. So what is time invariant? Time invariance simply says that the properties of a system do not change with time. For example, if I have a system which gives me, let's say, an amplification of input signals. Now let's say I have an audio amplifier. Now I give a signal to it, it amplifies by, let's say, twice the amount. If I turn on the machine today, it will amplify by 2 times. If I turn it on, let's say 10 days from now, still it will amplify the machine by 2 times. It's not going to change with time. So such a setup is time invariant. Whereas let's say now I have a battery. Today it gives me 1.5 volts. Tomorrow it gives me 1.5 volts. But 10 years from now it may still not give 1.5 volts. It might reduce it to 1 volt, let's say, or 1.2 volts. It reduces over time. So which means it is changing over time. It is varying over time. Such a system is time varying system. So any system whose properties keep changing with time, or the values of the system or the configuration of the system, if that changes depending upon the time in which you observe the system, then such a system is time varying system. Time invariant systems are good because if I analyze the system now, if I completely understand every property of a system now, then I can not redo this operation again and again. I need not keep analyzing it again and again. I can analyze it once and then keep using that model forever in time, because that model will not change. The system is not going to change itself over time. So hence time invariance is a very nice property to have for systems. Okay, how to check if a system is time invariant or not? The way that we are going to check is, you take any signal x of t and then you just arbitrarily delay it or advance it. If you are arbitrarily delaying it or advancing it, then you are changing the signal properties in time. If a time invariant system is fed in such a signal, it will always produce an output which is also correspondingly delayed or advanced. What does that mean? So it means that you can delay the signal and feed in a delayed version to the system. It should produce an output which is exactly the same as feeding in the original signal to the system as the input, and then observing the output and then delaying it. So if both of these have the same outputs, then we say that such a system is time invariant. So what does this actually mean? It means that the system properties have not changed over time at all. So if I have a signal, let's say a rectangular signal, and then I feed into this system, and let us say it converts this rectangular signal to a triangular signal. That's what the system does. Then the system description is such that whenever you feed in a rectangular component, it will change it to a triangular component. That's all. So if I delay that at the output, then I get a delayed triangular signal. Okay, let's say from 1 to 2. Because this system is time invariant, if I feed in a signal at some other time, let us say t is equal to 1 to 2, a rectangular signal which is now delayed. Let's say we feed in this. The system, all it does is changes a rectangle to a triangle. So it's still going to do the same thing. For it, it doesn't matter where the rectangle comes. Whenever it sees a rectangle, it will change it to a triangle. So as you can see in this example, this system is changing a rectangle to a triangle, and that rectangle can either appear at 1 to 2 seconds or minus half to plus half seconds. It doesn't really matter. So you can have this delay block either at the output or at the input. Both produces the same kind of system outputs eventually. So this is what we mean by time invariance. The system does not really care at what time I get the input. The output is always a fixed function of the input. So as you can see here, if the system is producing an output of y of t for the signal x of t, then the signal should produce an output of y of t plus capital T for an input which is x of t plus capital T. In other words, this signal is strictly dependent, the output signal is strictly dependent only on the input signal and not on the time at all. The system processes the input signal depending only on the values that are taken by the input signal and not on the value of the time. In other words, this system is not a function of time, it is a function only of the input signal. Okay. So now we saw what is a time varying system, time invariant systems, and then we saw how to find out a time invariant system, to how to find what is a time varying system. What is a time varying system? It has a different input output relationship at different points of time. So today if I see for an input of let's say 1 volt, it produces an output of 2 volts. Tomorrow for an input of 1 volt, let's say it produces 3 volts as the output. Then this is a time varying system. I cannot simply see what is the output today and also decide that tomorrow I'll get the same output. It was a time invariant system. Then I know that if I feed in an input of 1 volt today and I observe an output of 2 volts, I can shift my input in time to tomorrow. That is, I shift my time of input to 1 day by 1 day, and I see the output tomorrow. I know that it will also be the same output of 2 volts because it was time invariant. If it changes to 3 volts, then depending on which day I take the measurement, the output is changing. So it is a time varying system. So analytically or mathematically, how do we verify this? If the input x of t produces an output y of t and the input x of t plus t is not producing the output y of t plus t, then such a system is a time varying system. Essentially, such systems are not only functions of x, but they are also functions of time. Okay, so this y of t depends not just on x of t, but it also depends on what t is. Okay, so because of this reason, if you shift in time, it is not necessarily the same as without shifting in time. Advancing the signal or delaying the signal causes the output to change. Such systems are time varying systems. Let's see some examples. Okay, let's take this very simple example where the input is simply multiplied with an exponent like this and then the output is produced. Now we know this is the output at t. Now what if I feed in x of t plus t? So x of t plus t will produce y of t equal to e power minus t times x of t plus t. But this is not equal to y of t plus t, which is equal to e power minus t plus t into x of t plus t. So this is a time varying system. As you can see here, the output is not just a function of x of t, but it is also some function of time and the x of t. So because it is some function of time here, it is going to change with time. In other words, here the output is just a scaled version of the input. But what is the scaling factor? That scaling factor keeps changing with time. So at t equal to 0, this is 1. But t is equal to, let's say, 10, this is 1 by e power 10. So depending upon what is the value of time, it keeps changing the scaling factor, and hence this is not a time invariant setup. Now let's see this example. Okay, now what is the output of this system when you give x of t plus capital T as the input? In that scenario, y of t is integral minus infinity to t x of v plus capital T. But is this the same as y of t plus capital T? What is y of t plus capital T? It is minus infinity to t plus capital T x of v dv. Okay. Now let's change this variable of integration. Now let's say that w is equal to v minus capital T. Okay. In that case, what happens to this entire integration? Then you can say that dw is still equal to dv because capital T is just a constant, and when v is equal to t plus t, w is just t, which means the limits of integration will become minus infinity to t, and v is nothing but w plus capital T times dw, right? Which is exactly the same as what we have here. So this is a time invariant system. So even though immediately it looked like a time varying system, when you work out, it turns out to be a time invariant system. So this is nice, at least the differentiator and the integrator, both these systems, which we often encounter in practice, are time invariant systems, which is good. Let's see some more examples. Okay. Now, is this a time invariant or a time varying system? So remember, as long as the output is a function of the input alone, it's time invariant. But in this case, it is getting multiplied with some other function which is not the input but which changes with time. So obviously, just by observing it, we can say that this is time varying. But let's verify, right? How do you verify? X of t produces the output x of t times ut. Now x of t plus t, what is the output? X of t plus t produces an output x of t plus t times u of t, which is not equal to x of t times u of t, right? So simple case, let's take rectangular function. So if you feed in the rectangular function, the signal is multiplied with u of t and you get an output. If this was x of t, then the output is just this, the positive side. Now let's say you feed in a shifted version, shifted by plus 1, which means it moves to the left side. Now this is x of t plus t. What happens to the output? The output is fully 0, which is not the shifted version. It is not the shifted version. Hence, this is a time varying system. Okay, so let's see what happens when the input is just time scaled and time shifted. Okay. Now first let us assume that this a is not equal to 1. We'll see why this is important later. Now as usual, let's feed in a time shifted version. If you feed in a time shifted version, then what is the output? Then the signal x of t plus capital T is time shifted and scaled. So all you have to do is, instead of shift being plus b alone, you also have to include this plus t. So now the shift is going to be plus t plus b and time scaled, right? This is what you will see as the output when you feed in a time shifted version as the input. The shift at the output is going to be slightly more because the input is also shifted. So this is like saying I'll feed in x of t to a time shifter which increases plus t, and then to another system which increases plus b and then scales time by, right? this is as good as saying I will shift by t plus b and then scale with at. Correct? That's what we have here. Alright, but is this equal to y of t plus capital T? It is not, because y of t plus capital T is in fact a times x of a of t plus capital T plus b. Right? So here the shift is at, but here, whereas here the shift is only plus t. So both are not equivalent. Both are equal only when a is equal to 1. Remember, so that is why this comes in as important factor. So when a is not equal to 1, this is time varying, and when a is equal to 1, it is time invariant. So this system for a is equal to 1 is time invariant. So what if a was just 1? Then there is only time shifting. So if a was 1, then we have x of t is just simply the time shifted version. So x of t plus capital T is now going to produce x of t plus t plus b. So it clearly means time shifting operation is time invariant. Time scaling, if it is not scaled by 1, then it is time invariant. So what about minus 1? Even that actually makes the system to be time invariant. So let's see a very simple example. Remember, we took this signal often earlier. Let us say this is x of t. Okay, and let us say that we are going to time shift it by 0 and time scale it by 1 and amplitude scale it by 1. Now the output is simply going to be the time reversed version. Right, this is the output, which is equal to x of minus t. This is minus 1, 0, 1. Now let us shift the input x of t plus 1, meaning it's going to move to the left. Now feed it to the system, which produces this output of time reversal. Remember, all we are going to do is time reversal, right? So this is the system x of t plus 1, where there is only time reversal, meaning this is x of minus t plus 1. So this is going to be the output, whereas what was the shifted version of the output, t plus 1? It is actually something else altogether. The shifted version of the output looks like this. So both of these are not the same. Clearly, they are not matching. Hence, this is a time varying system. All right, now let's see the next example. So the next example, just by looking at it, you can say it is a time varying system because there is a t square term, which means that depending upon what the value of time is, the amplification of the signal changes. At time t equal to 0, the signal output is 0. Time t equal to 1, the amplification is 1. Time t equal to 2, the amplification is 4. It is going to keep changing with time. Okay, so we can verify this by taking x of t plus t and then checking what happens. Let us check what happens. So it produces an output which is t square x of t plus capital T plus c, which is clearly not the time shifted version of y of t. Why is that? Because y of t is equal to obviously these two are not the same. Hence, this is a time varying system. Okay. Alright, so let's see what happens to this setup. So x of t plus t produces tan of x of t plus t. Clearly this is function only of the input, nothing else, right? This is still going to be equal to y of t plus capital T, which is the same, and hence this is time invariant. What about this setup? So you feed an x of t plus t. This is dx of dt, which is the same as shifting the output also, right? Hence this is also time invariant. Now what about this scenario? You are taking the product of two signals. One is a delayed version of the other. What happens here? If you shift by, let's say this is t naught, then x of t plus t multiplied with x of t plus t naught, which is once again the same as y of t plus t. Hence this is also a time invariant system. So as you can see, as long as the output depends on both the input and another function whose value changes with time, we see that the system is turning out to be a time varying system. Whereas if the output depends purely only on the input and nothing else, then the system is a time invariant system.